Welcome, my dear class 11th students and even the class 12 students who want to cover up the backlogs. We are on to the lecture number 3 of work power energy, mechanical energy and conservation, and of course the power concept. Before this, we have talked about what is work, what is kinetic energy, the work and kinetic energy theorem, also conservative, non-conservative forces, the concept of potential energy. All of this was done in the previous classes. So time to move on. All my JEE 26 and 2027 students, I hope you are all geared up with your Captain Shreyas Sir. Hi Sajja, hi Bhupati, hi Dhima. Welcome everyone, join in. Yes, the class has just started and we are going to begin. And I hope you have also registered for MVSAT. In case you haven't, please do that right away, right now, because it's not just about the prizes or the scholarships, but it's also about the free study material that you are getting after you register, which is very simple and free of cost. And number two, that you are going to get your national ranking in your grade where you stand, because this is the most widely written exam across the country. So you will know where you stand, you will know what to work on, you will know your strengths, and you will know exactly what to do ahead. It's very important that you face the competition beforehand only, because these are the exact same kids who are going to write the exam with you, right? So let's begin. Adarsh, welcome aboard, and let's do a quick recap of whatever we have done till now, and then we'll proceed. Remember, we have talked about kinetic energy, which is nothing but half mass into v square, or p square divided by 2m. We have talked about this. Then we have also talked about work, which is force dot product with displacement, or you can also use integration of force with displacement if it is a variable force. If it is a variable force, this is used generally for constant force. Then we related work and kinetic energy. We said that whatever the total work is done by all the internal and external forces, that will give you the change in the kinetic energy, which is final minus initial kinetic energy. This is what we done on the day one, if I'm not wrong. Then we went on to potential energy concept, and we said that potential energy is the ability to store energy and capacity to do work. It can decrease, increase. It always tries to lower itself though, because more potential energy means it will be very unhappy. Like a stretch spring will be unhappy because it has more potential energy, but you release it, it becomes very happy about it by lowering the potential energy. And we saw the formula for potential energy difference of gravity, which is nothing but mg into h, and the potential energy of a spring, which was nothing but half spring constant into x square. This is what we have seen in the previous lectures, right, everyone? And there is a beautiful relation between force and potential energy, if you remember. Yep, the work done by the conservative force, the negative value of it is the change in the potential energy, and using this only we got the conservative force. The conservative force is negative rate of change of energy with respect to distance, du by dr, not dt, it is dr. Okay, these were some interesting relations which we got in the previous classes. All right, so it's time to now move ahead and then talk about the next concept, which is nothing but mechanical energy. Now, this is very interesting. Okay, what is mechanical energy? Mechanical energy is nothing but it is the sum of kinetic, it is just the pure sum of kinetic and potential energy. That's it. It's like a total energy concept only, but I'm specifically going to take kinetic and potential energy only. Do not take light energy, chemical energy, muscular energy, biological energy. Other energies are not counted. Only if you take kinetic and potential energy and add them up, that exactly is mechanical energy. Hi Kishore, good evening. Prabha, today is the last session of work power energy. Yeah, that's it. This is the last session. Now, let's say for example, we have a ball. Okay, we have a ball over here which is thrown and it is going like this. We know that as it moves, its speed will change, its height will change, so its kinetic energy will change, its potential energy will change. So this ball at any moment, because of its motion, has its kinetic energy, and because it is at some height, because it is at some separation on Earth, it is at some height on Earth, because of that, it also has gravitational potential energy. So both of them combined together, if I see how much mass, how much speed it has, I can measure kinetic energy. If I measure mass, G and H, I will get potential energy. If I add them up, what I will get is the mechanical energy. So their total is what is going to give me the mechanical energy. Is that absolutely clear? It's simple addition. So if you ask me, what is the formula for mechanical energy? The formula for mechanical energy, my dear students, the formula for mechanical energy, E mech will be nothing but kinetic energy plus potential energy. That's it. There is nothing great about it. It's very laddu looking formula. Just kinetic energy plus the potential energy. This also means that if at all, for some reason, I have to find the difference in the mechanical energy, how much has the mechanical energy changed, I will figure out how much has the kinetic energy changed and how much has the potential energy changed. And if I add their changes, I will get the total change in the mechanical energy. So this gives me how much is the change in the mechanical energy. How much is the change in the mechanical energy simply. Is that okay, everyone? Till this point, absolutely clear? Give me a thumbs up right away, right now. You studied Manju in the Vedantu JEE English channel, and I cracked JEE now studying in NIT Trichy. Oh my God, Manju, this is so good. Why don't you put it up as a comment, bro? It will be amazing for the juniors to watch that comment, right? It will be very inspiring and motivating. There's a lot of students from Tamil Nadu do watch our classes out here. And when you talk about NIT Trichy, the topmost NIT, they will also feel very inspired and motivated. Just put up a comment after the session, right? All right. Great. So let's see where mechanical energy can change, where mechanical energy may not change, all these kind of scenarios. And that is what brings us to the conservation of mechanical energy concept. So let's take some examples. All right. Say for simplicity, imagine there is some mass over here and it is moving with some speed like this, okay, on a flat surface, on a smooth flat surface. Now what happens is, as it moves ahead, there is a spring which is connected and it's connected to a wall. The spring constant is K. This surface over here is perfectly smooth. There is no friction at all. In the second scenario, the difference is there is no spring and this surface happens to be rough. This surface happens to be rough with a coefficient of friction mu. Let's understand what will happen in either of these two scenarios. As this block moves, tell me, will the gravitational potential energy increase or decrease? It's going on a flat surface. So the gravitational potential energy, if you ask me, that will not change. It will remain constant because it is neither going up nor is it going down. Perfectly fine. What do you think will happen as it hits the spring? The spring will get compressed. The spring will store the potential energy. So the spring potential energy will increase. So if you ask me about the spring's potential energy, 100% I will say it will increase. It will increase as it compresses. As it compresses. Okay, here it was constant because it was going horizontal. It was horizontal motion, so there was no change. What do you think will happen to the speed? As it hits the spring, it will slowly start slowing down. The speed will reduce. So the kinetic energy will decrease, correct? So if you ask me what will happen to the kinetic energy, the kinetic energy will 100% decrease as it slows down, as it slows down. Okay, perfect. So kinetic energy is decreasing, spring potential energy is increasing, gravitation wise there is no change. If you ask me to total all of them, that will give me the mechanical energy part. What is happening to the mechanical energy? Can you guess what will happen to the mechanical energy, my dear warriors? The mechanical energy will remain the same. Yes, because the spring will the spring will increase the energy potential wise, but kinetic wise, it is reducing. So the reduction in the kinetic energy is compensated by the increase in the spring potential energy. So overall, the energy level is maintained, right? It's like 5 rupees fell out of one pocket, but in the other pocket, somebody added 5 rupees. So as a whole, you have the same amount of money. So kinetic energy was reducing, but potential energy was increasing. It compensates and it nullifies. So the mechanical energy remains conserved in this scenario. The mechanical energy remains conserved in this scenario. Is that right? Everybody with me? All right. Okay. I'm Syamla, I'm studying in this batch, but I can understand my explanation. Can I able to change the Sigma batch? No, you cannot change the batch internally. You will have to buy it separately because these batches are very low price batches. So there is no such, so many facilities are not there, bro. It's mainly focused on the teaching, content, testing, assignments, teachers. So that's how it is. So right now, you can buy the batch for 1999 rupees on sale because of Teachers Day. I hope if that is convenient for you, you should definitely consider that. Okay, Samla? All right. Now, in this example, mechanical energy was conserved. Let's take another example right over here. This block, as it moves on this rough surface, let's think what is happening to its gravitational potential energy. Well, it is neither going up nor going down, constant height. So obviously it is remaining constant. And the reason for that is its horizontal motion. Okay, sir. What about spring? Spring is only not there, bro. Which spring is there? Nothing. Oh, so no other potential energy, as you can see. Sir, friction is there, sir. Frictional energy. There is no such concept called as frictional energy, right? I hope you remember friction is a non-conservative force. So whenever a force is non-conservative in nature, I mean, it does not have any, concept of potential energy like normal energy, tension energy, frictional energy, viscous energy, air drag energy is not there. Gravitational energy is there, spring energy is there, elastic energy is there, electric potential energy is there. Those are conservative forces, great forces, good forces. Okay. What about our kinetic energy? Kinetic energy is obviously reducing, and the reason why it is reducing is because it is slowing down. As it slows down due to friction, as it slows down due to the frictional force. Oh, this is going to be very interesting now. Now, if I add them up and if I count how much is my mechanical energy, what do you suggest? Is it going to be conserved now? Is it going to be constant like before? Here it was conserved, or basically I can say constant. All right, it was maintained, it was preserved. Conserved means preserved. Here, I don't think it is preserved because gravity, fine, it is preserved, but kinetic is reducing. So any one of the two reduces, the total will reduce. This reduces or this reduces, this will reduce. Both are constant, this will be constant. This increases, this reduces, this will be constant. But obviously one of them will reduce, this will also reduce. So definitely over here, I can clearly say that the mechanical energy is reducing, and it is not conserved. It is not conserved. Now, usually I have seen many kids say that mechanical energy is always conserved. And universally, no matter where you go, mechanical energy is always an universal principle. See, don't get me wrong. Sometimes teachers also explain in some weird way, but that is not true. And I've just demonstrated that mechanical energy is not conserved. It is in fact the total energy in the universe along with the mass which remains conserved. Mechanical energy may be conserved, may not be conserved. Because mechanical energy is just two kinds of energies together, which is kinetic and potential. But when you talk about total energy, that accounts for heat energy, mass energy, this energy, that biological, muscular, all forms of energy. That total energy, no matter which scenario, has to be conserved. There are no absolute exceptions for that. It's a universal law. But mechanical energy has its own conditions, ifs and buts are there. Now you might be wondering, okay, fine, sir, I accept that. But then, how do I know whether it is conserved or not conserved? Will I have to do this kind of analysis? Will I really have to check till the end? Oh, this much was there before, now it is not there. Oh, it is not conserved. Oh, it was this much here. The same is there. Oh, it is conserved. No, no, no. You don't have to do so much of calculations. Just looking at the scenario, you can predict whether it will be conserved or not. Maybe you can take a guess now. Look at this scenario versus this scenario. Why do you think energy was conserved mechanically versus why do you think it was not conserved over here? What is that reason? Some students might start thinking and start saying that, sir, it is friction, sir, I know that is the culprit. Well, you are right, almost on to the point, but friction, is it always going to be there? No, but still there are chances that mechanical energy will not be conserved. See, friction is an evil force. So these evil forces are the problematic forces. So students ask, do you mean non-conservative forces then? Absolutely. I'm talking about non-conservative forces. And if these evil forces are there, what happens when villains come into life? Things go bad, right? Yeah, you will start losing money. So same thing when the villains of our physics, which is friction, air drag, air resistance, viscous force, air drag means that fluid friction, okay? Normal force, tension force. Whenever these people start coming into your life, they are like that Rahu Ketu. You have to do puja. So they will start basically creating problems. They will not conserve the mechanical energy. Oh, sir, but if you are saying like that, then at this point of time, I have another doubt. Friction is there. Okay, gravity is conservative, so let's not worry about it. Normal is there. And in this problem, weight was conservative. The spring force, whenever it comes, okay, that spring force will be conservative. And here you have normal. If you see normal mg was there. Here the only difference is there was kinetic friction versus here this is not static friction, this is spring force. Don't get confused. Okay, this is spring force. So this spring force was conservative. So that made a big difference. That's why mechanical energy was conserved. But here kinetic friction was non-conservative. That's why the mechanical energy was not conserved. Okay, non-conservative, not conserved. Conservative, conserved. Simple, equal. Okay, if the non-conservative forces are there, mechanical energy is not conserved. Conservative forces are there, mechanical energy is conserved. Sir, but you know, I have still a problem. This normal dude is there, and the normal dude is non-conservative in nature. So how the hell did you conserve mechanical energy? Right? Very good question if you are thinking in those lines. So here is the catch. Normal force is there here also. And it's an evil force. It's non-conservative. How the hell did mechanical energy get conserved? Any guesses out here? JP, it's up to you, man. It is obviously enough. There are many kids who crack it. Yep. All right. Hi, BCD. Good evening. Yeah. Yes, solving problems, but still not able to confident. JP, you can put it up as a comment. Maybe I can answer it separately. Sir, in this series, work per energy will be completed from 0. Yes, HSEC. This is the last class of, yeah, work per energy. Both potential and kinetic compromises evenly. Yeah, whatever is the reduction prabha is the increase in the other. Hi, Vishal. So, here is the answer to this. Even though normal force is non-conservative, as you can see, as this mass moves, the displacement is perpendicular to the normal. So the normal force is not doing work. Yeah. So even if non-conservative forces are there, if it doesn't do work, then mechanical energy is conserved. Simple rule. So till this much detail, I am pretty sure many YouTube channels do not cover. They just do it at board level. Mechanical energy is conserved, kinetic energy decreases, potential energy increases, total energy is remaining constant. That's done. All this will happen. Then nobody will tell you, and this is where people fail in JEE. So let's write down the actual rule. The mechanical energy of a system is conserved only if the non-conservative forces don't work if present, if they are present. Mathematically, I will write it like this. Mathematically, I will write it down like this. If the total work done by non-conservative forces is equal to 0, then E mechanical, the mechanical energy change will not be there. Mechanical energy will be conserved. Or you can also say initial kinetic energy plus initial potential energy will be final kinetic energy plus final kinetic energy plus final potential energy. So if this is true, then there is no change in the mechanical energy. That is, the total sum before and the total sum afterwards will remain the same. And this only happens when non-conservative forces like friction, viscous, normal, tension, they do not perform work. Only then this equation holds true. So if you use this equation out here, and if I say that, listen bro, kinetic energy initially plus potential energy initially is kinetic energy finally plus potential energy finally, then how will my equation look like? Initial kinetic energy is half mv square plus potential energy initially, I don't know, it will be there something, I don't care. Let's say you assume it as u naught. Spring wise, it is not there. So gravity wise, it was there. So I will not actually write the gravitational energy, because see, even if I write the gravitational energy, I know it is going to come here also. Anyways, any which ways, it is going to get cancelled. So why do you want to waste your energy in writing a term which is anyways going to get cancelled? Okay. On the right hand side, kinetic energy will be 0, because once the block compresses the spring, it will stop. It will move like this and stop. So once it stops, kinetic energy will be 0. Spring wise, there was no energy here, but once it compresses on the right hand side, I should put half kx square. So initially it had kinetic energy. All that kinetic energy got used up into storing it in the form of spring's potential energy. Gravity wise, no change. It was constant. That's what is evident even in this equation, which you can see it is getting cancelled. So half goes off, and you will see mv square will be kx square. Therefore, x will be equal to v root of m divided by k. So this is how much the compression, this will be the maximum compression in the spring, when the block stops, when the block will stop, right? So this is how you can use energy conservation to solve the problems. Is that absolutely clear? Let me show you one more example, guys, for energy conservation where mechanical energy is conserved. This is a beautiful demonstration of it. Say, for example, in projectile motion, where you throw an object from a hill and you would have thrown it at different angles, whatever. Say, once you throw it like this, then next time you throw it like this, then next time you throw it like this, next time you throw it like this, next time you throw it like this. Out of all these scenarios, Obviously, it will take different paths, as you can see. One path might be like this, another part might be like this, another it might go up and then it might come like this. This it will just go and come over here. Yeah. So yeah, something like this. So maybe I'll just show it with a line. And here though it will just directly come off like this. So all these are the different projectiles. If every time I'm throwing it with the same speed, assuming same mass, which will come down the fastest, who will land on the ground the quickest or fastest? Think about it. This ball will come down really quick because it has to go very short distance and you are throwing it also in the same direction. But this ball, it has to first go up and then come down. I think this will take the longest amount of time to fall down. And this will increase sequentially from here to here. Like this will be the fastest to land. Then this will be the second fast, third fast, fourth, and this will the last ball to land on the ground. Time wise, every one will take different time to touch the ground surface. But if you ask me the speed, right, that's where the funny thing is. Speed wise, no matter which ball you take, all of them will land with the same speed. We're like, what the hell? How, sir? How can it happen? How can they all land at the same speed? Okay, how can they all land at the same speed? See, the reason for that is in this particular problem, there is no friction, air resistance, etc. So mechanical energy is definitely conserved. Mechanical energy is definitely conserved. Is that clear? Friction, etc. is not there. So if you ask me what is initial kinetic and initial potential and then equate it to final kinetic and final potential, we will get the answer. Initially, the kinetic energy is half mu square. Potential, I'm at a height of mgh, so I'll put mg into h. Here, the kinetic energy is half mv square, and when I'm on the ground level, the potential energy, I'm taking it as 0. Cancels, so I'm just getting u square by 2 plus gh is equal to v square. So therefore, I can just, v square by 2, multiply by 2. So v square will be u square plus 2gh. Therefore, v will be root of u square plus 2gh. So this tells me doesn't matter what the angle is, the speed at the point of or at the ground impact will always be the same. So it's not dependent on the angle. So this is very crucial. It is independent of the angle. Independent of the angle of projection. Time will differ. Yes, the time will be different. The time of flight is different for all, obviously, but the speed of impact on the ground, it is the same. All thanks to conservation of energy. Is that absolutely clear? Oh, yes, I am also from Salem, man. Hi, Subha. Hi, Tharuna. Hi, Chitra. Good evening. Good evening. Very good. Excellent. All right. The time of ascent will also be different. Some of them will not even go up like this and this. It's not even going up. This is just coming down. This is just coming down. Only this and this is just going up for some time, right? Yeah. The time of ascent and time of descent will also be different. Like it's going up only for this much time, but it is coming down for a longer time. So that will also not be equal. The time of ascent and descent are equal only when you throw it from the ground and it comes on the ground. Not when you start from here and then you measure from here and then coming down is different. Okay, so that is how mechanical energy can be conserved. But sir, can you tell me what to do if mechanical energy is not conserved? No worries. Here is what we will do. So if 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 the total work done by non-conservative forces is not zero, then a simple thing. Then all you have to do is whatever is the initial kinetic energy plus the potential energy will be equal to, okay, it will definitely not be equal to the final plus kinetic energy plus potential energy. There will be some work done as well. So think of it like this. Whatever work is done by the non-conservative force, that will cause a difference in the mechanical energy. And when I say difference in the mechanical energy means there will be a difference in the kinetic energy and difference in the potential energy. Difference means final minus initial. Final minus initial. Bring these people over here. So therefore, you will see that initial kinetic plus initial potential plus whatever work is done by that non-conservative force will be the final kinetic energy plus final potential energy. So this is what you will get in case that work is there. So this is more like a God formula, because if energy is conserved mechanically, then this guy will be 0. So this will not even come. But if this person is involved, then you can just modify the equation and you can still solve the problem. Let me demonstrate that to you. Say for example, this one only. Here, non-conservative force, which is friction, is definitely there. So what do? We will say, okay, initial kinetic plus initial potential plus work done by non-conservative force will be final kinetic plus final potential. Initial kinetic energy, half mv square. Initial potential energy and potential energy here, it is the same, guys. I mean, just think about it. Gravity wise, it has not changed. So if I put ug over here, I have to put ug here also. I know it will get cancelled because it has not even changed. So don't bother also putting it. Anyways, then on the final side, see what will happen. This will eventually stop. So final kinetic energy is going to be 0. Okay. Now only this part is left. Friction is going to do negative work. So the work done by friction will be negative, the frictional force multiplied by the displacement. Let's say it is x. All right. So therefore, I will get half mv square is equal to kinetic friction into x. Kinetic friction will be mu mg into x. So this is nothing but half mv square. Cancels. So therefore, x will be equal to v square by 2 mu g. So I figured out how much distance will it take to stop, knowing the speed, friction and g. So you can find the stopping distance on this surface using again the principle of non-conservation of energy. Okay, non-conservation of mechanical energy, you can say. So this is a modified formula. Okay, many books will not give you. I'm giving it to you. It's there in some, foreign author books and even the proper JEE advanced books that will have this kind of equations. But if you go to some laddu paddu books, you will be confused. What are they doing? Okay, so all these are very, very important. Even this one, obviously, when is this conserved? Only when this word is very important. If the work done by non-conservative force is 0. If it is not 0, no issues. You add that over here and then solve the problem. Cool, guys? Everybody? All right. Thank you. Welcome, Hansika. Do we have MCG sensitivities like current sensitivity and voltage sensitivity? Yeah, we have that. We'll do that later on. Sir, why are we take as potential energy gravitation? Because Abhijit, no matter where you go, gravitational potential energy will exist. In this case, it didn't change because the levels were same. But if it is going up or coming down, then UG would have changed. Just because it didn't change, it didn't matter here. So it doesn't mean you shouldn't consider it. I just wanted to realize that, listen, bro, it just got cancelled. But maybe in some other case, it could be different. And that's what we might see. Say, for example, we do some more questions coming up on your screen. But before that, let's take up some simple, easy peasy ones. A particle is placed. This was J24 question. A particle is placed on a frictionless track, ABC. It is like a H.C. Verma question. The speed of the particle when it reaches the point B is how much? Okay. So let's understand. This particular particle, right, when it comes down over here like this, okay, this is that particle, it is going to experience some forces like weight is going to be there. Now mg is going to be conservative in nature, okay, not an issue. But the problem is the normal force, and this normal force is non-conservative in nature. And it is also mentioned it is smooth, frictionless, so friction is not there. But imagine this block or this particle is going like this, the displacement is this way. So even though the force of normal is there, it is not doing work. so I am safe. It is not doing any work. It's like virus is there in your body, but still you are not sick because the virus is dormant. So it is exactly that scenario. Okay, so I can definitely say that initial kinetic plus initial potential energy is final kinetic plus final potential energy. Now here I do one strange thing, or not very strange. I will take this level as my zero reference. Why? Because that is better. Then I can say all the particles here have zero potential energy. So now the height difference that will be involved is just 0.5 meters. Okay. Initially, it is just gently pushed. Gently pushed means the initial original kinetic energy will be zero or negligible. Potential energy wise, mgh, mass, I'll just take it as m, g is 10, height is 0.5. Finally, when it reaches here, it will have some speed. So that's what we have to find, half mv square, plus potential energy when it reaches on this level, point B, it will be 0. Okay, so this entire thing is at point A and this entire thing is at point B. Realize that. Mm gets cancelled, 10 into 0.5, that's 5. That's V square by 2. Okay, so V square is 10. So therefore, V is root of 10 meters per second. Root of 10 meters per second, that is option labeled 2. Perfect. JEE 24 question. This kind of laddu question had come. Can you believe that? Yeah. Perfecto. This is how you use mechanical energy conservation. Let's go to another question. Now, I think in this particular question, mechanical energy may not be conserved because I can see some friction and all that is involved. Okay, beautiful. So, block is simply released from the top of an inclined plane as shown. The maximum compression in the spring when the block hits the spring. Wow. So, the block slides, it goes on this rough patch, only this much part has friction, and after that also some speed might be left, and then it hits the spring and then it stops. So in this entire scenario, it's very evident the friction which is there, it's the evil part which is not conserving the mechanical energy. We have to go with the basics then. Let's start. Maybe I'll create a duplicate over here. Okay, perfect. I need some space. Just creating some. So I will say that my initial kinetic plus initial potential energy plus the work done by friction is going to be final kinetic plus final potential energy. And the reason for me to say that is friction is non-conservative and doing work, and it is definitely going to do work. In this particular part, the frictional force which will be involved will be mu into n. Mu is 0.5. Normal force will be mg. Mass is 5 and g is g only. So g into 0.5 will make it 5. 5 5s are 25. So this will be 25 Newton force. 25 Newtons of frictional force is going to be there in this particular region. Which region? This rough patch which is there over here. In this region, that friction is going to there. After that, it's going to hit the spring. So let's start right from here on the top. So this part is basically for the top part, and this part is when there is maximum compression in the spring. Okay. So at the top part, what kind of energies are there? Kinetic energy, negligible. It's just starting. So 0, of course. Okay. Spring wise, there is nothing. It is not even compressed. But gravitational is there. See, this U not only stands for gravity, but also for spring. It is a complete picture of potential energy. Okay. Don't just take gravity or don't just take spring energy. Whenever that U is there, it means the total potential energy of the system. So you cannot miss anything. So spring wise, there is nothing. Spring wise, sorry, there is nothing, but gravity wise, there is something. Oh, we need to measure the height, is it? So how much will that height be? Think about it. Yeah, how much will this particular height be? This is 10, this is 30. So obviously, this particular height will be 10 sine 30. Sine 30 means half. That means it will be 5 meters. 5 meters. Okay. So gravity wise, m into g into height, which is 5, plus work done by friction. Frictional force is 25 newtons, displacement is 2 meters, and it is negative work. Why negative? Force and displacement are opposite in nature. That's why the work done will be negative. If it was a non-conservative force doing positive work, I will accordingly add it. That's all. Final kinetic energy, it will stop after maximum compression. It will come and finally hit it and eventually press it and stop. So once it stops, kinetic energy is 0. Spring wise, the energy will be half into K. K is 100, I believe. 100 multiplied by spring extension or compression square. Gravity wise, there is no energy at all. Why is there no energy? Because again, let me remind you, I am taking this particular level as zero reference for gravity. Zero reference for gravity. So here it had energy which was mgh, but when that same block came down, it is at the zero level, so no energy at all. Perfect. So let's solve this now. G is 10, 5 5s are 25, so this is going to become 250 minus 25 into 2 is just 50 is equal to 100 by 2 is basically again just 50 multiplied by x square. 250 minus 50 is 200. So 200 is basically 50 times of x square. So 50 comes below 200 becomes 4. So 4 is x square. So x is naturally 2. So 2 meters will be the final answer, as you can see over here. 2 meters is the final answer. Understood, guys? This is how you conserve mechanical energy. Very straightforward. Good evening, Pritija. Very good, Sandeep. Amazing, amazing, amazing. Now, these kind of questions you will also see in circular motion. So once we do circular motion, those vertical circular motion questions will become very easy using mechanical energy conservation principle. Okay. All right. Let's do more questions coming up on your screen. Here it is. Imagine a ball of 200 grams is dropped from a height of 20 meters and touches the ground with speed of 10 meters per second. Find the work done by air resistance. Find the work done by air resistance. Beautiful question. Let's see if you guys can figure it out. Let's imagine this. This is our ground level. This is that ball. 200 grams means 0.2 kg. The height is given to be 20 meters. Okay. And when it hits the surface over here, it is hitting at 10 meters per second. It looks like very small speed, maybe because friction has done some work. Air friction, air resistance. Question is to find the work done by the air resistance. Quickly think and tell me in this question, obviously mechanical energy can't be conserved. Because why else would they ask what is the work done by air resistance? And air resistance is a non-conservative force. So air resistance is non-conservative in nature. And whenever you have non-conservative forces which are doing kind of some work, then I will say initial kinetic plus initial potential plus work done by our non-conservative forces will be final kinetic plus final potential. Okay. When I drop this, obviously it had no speed, so kinetic energy will be 0. Potential energy wise, obviously it will have the potential energy which is mgh. M is 0.2, G is 10, height is 20. That's it. Plus work done by the non-conservative force. That is exactly what we have to find. Work done by air resistance. Final kinetic energy is half into mass, which is 0.2 kilos, into the speed square, plus potential energy, gravity wise, is 0 over here because it has come back to the ground level. Okay, let's do the math over here. 0.2 into 10 is 2. 2 into 20, it's 40. Okay, plus work done by air is equal to, now this 2 and 2 will cancel, this will become 0.1. 0.1 into 100, that is going to make it 10. Is that right? Everybody with me? Okay, so what is the work done by air? It will be then 10 minus 40, which means it will be minus 30 joules. So the air resistance has sucked out 30 joules of energy from that ball, and that's the reason why mechanical energy was not even conserved in the first place. Got it? Very good. So the answer will be minus 30. If there are two options, one is plus 30, one is minus 30, you will better mark minus 30, or else you will get negative marking for missing that sign. Okay, it's sucking away the energy, so negative work. Okay, is that absolutely clear, my dear warriors? Perfecto. Can we go ahead? Yep. Amazing. Okay, right. Pritija, for understanding the question, I would say there are 2-3 tricks and tips. One is read the question in parts. Sometimes reading the question in parts might be also tricky. So always look for the conjunctions like but, which, where, and, then, if. So those are the separators. Wherever that part starts, before that you read it separately, after that you read it separately. Second thing, draw rough diagram. Sometimes drawing one diagram might not be enough. You might have to draw before, after, then this, top view, side view, like that. Next, whatever you read, whatever you can understand from that question, label that. Mass is this much, speed is this much, direction is this much. And the most important thing, whatever you don't know, don't assume it to be at right angles, at some convenient 45-degree, or just take it as 0, or take it as something. Whatever you don't know, literally draw it in the most weirdest way, because or else your brain will start thinking, oh, this is 45-degree. Okay. And the last one, always do your rough work neatly. So that way, you'll not make silly mistakes while solving the question. Okay, I hope that's clear. Now that we have understood what is mechanical energy conservation, all right, and we have solved a couple of questions, let's go to the last final part, which is basically power. All right. Now, power is how quickly you do work, is how quickly is the work done. Like, for example, if you start studying for JEE preparation now in September, you will have to do the entire syllabus in 4 months, more power. But the same student who starts in 11th standard, he or she will get around 2 years. So less power. So that is less stressful, right? So same thing, the same effort, but you spread it over a longer time, it becomes convenient, easier. That same effort, you have to do it in a very short duration, it becomes very stressful. You have to apply a lot of power and energy on it. So that is exactly power. So power is simply dW by dt. Sometimes it's also associated with the energy equation. So work done, it is how quickly the work is done, or energy is flowing. How quickly is the energy flowing? So dW by dt, or we can say dE by dt also. dE by dt also. E stands for some kind of energy. All right. Now you can also further play with it like this. Work is nothing but force dot producted with displacement, and then what you do, take the time part below the displacement, and you all know what is ds by dt. It is rate of changing that displacement or position, which is velocity. So power is also force dot producted with velocity. Okay, force dot producted with velocity. Now please keep in mind, whatever formulas I am giving over here, all these formulas are for instantaneous powers. Instantaneous powers only. Instantaneous, at that moment. The force which is being applied at that moment, and the velocity which is there at that moment. Because this is instantaneous, this is instantaneous, this is also instantaneous power. As you can see, derivative is always associated with instantaneous values. So you will get instantaneous values of powers. But somebody says, no, sir, I want to find the average value of the powers. No issues. So for average values, for average calculations, here is what you need to do. For example, I want to calculate what is the average power involved. Then you will find the total work done. You will find the total work done and you will divide it by the total time taken. Now the total work done, remember, work kinetic energy theorem is the final kinetic energy minus initial kinetic energy, and if you divide it by the time, you are just going to get the average power. So either you know this or you know this with the time. That's it. That's how you can calculate the average power of that system. Okay. So for instantaneous, you can use either this or this, derivative or this. For average, you will use this. Let me demonstrate this with examples. But before that, the last thing, which is the units of power. So the SI unit of power, the SI unit of power is called as a watt. And a watt of power is when you do a joule of work in 1 second. So if you do 1 joule of work per second, it is called 1 watt. Usually the higher units are kilowatts, megawatts and all of that for electricity generators and all of that. So those are bigger units. But there is also another unit which is horsepower. So 1 horsepower, you will see it in the car engines or bike engines. So 1 horsepower is roughly 746 watts. And this is also related to the olden times because before the invention of cars and automobiles, people used to drive horse carriages. So when James Watt, James Watt, realized that mechanical energy can be created by heat, and the invention of automobiles thereby followed. Then people who wanted to migrate from the horse to the automobiles, they wanted to know how many horses equivalent is this. Like for example, when we right now are moving from petrol and diesel to electric vehicles, we want to know how much charge can the battery hold. Then when we say, oh, it has this much 74 kilowatt battery, you are scratching your head. 74 kilowatt battery means how much exactly? Then we say range. Yeah, this can go 500 kilometers. This can go 700 kilometers. Oh, okay, this can go 700 kilometers. I fill my petrol or diesel and my car will go 400 kilometers. This is also going that much. So it is almost the same. So, and that is how it is. And then we also talk about pricing. Okay, per kilometer, my diesel vehicle might take 10 rupees. Electric vehicle will take 0.5 rupees. So then you become happy. So same way during that time when the conversion happened from horse carriages to automobiles, they wanted to know how many horses is this automobile equivalent. So that is why this calculation has come. 1 horsepower is 746 watts. Is that clear? Yeah. Right. Dilip, this is the last session, right? Steam engine by James Watt. Yes, perfect. Good evening, Rudra. Yeah. Is power scalar? Yes. Why is it scalar? This is a dot product. I hope you saw this. This is a dot product, guys. Okay. Scalar product. Let's see some questions on to this. Coming up on your screen. Here it is. The first one. If velocity is t square I cap minus 4t j cap, mass is equal to 2 kg. Find power at t is equal to 3 seconds. Find the power at the instant of 3 seconds. Now we all know to find the value of the power, all I will need is force dot producted with velocity. The problem is I don't know force, but I know velocity. Velocity is t square I cap and 4t j cap. But that also I'll have to put with values. So before that, I think I need the value of the force. How do I find it? Think from velocity, if I have to find force, for force I need acceleration, and acceleration I can find through velocity. How? We all know that acceleration is the derivative of velocity. Acceleration is derivative of velocity. So it is just d by dt of this guy, which is t square I cap minus 4t j cap. Okay, let's find the derivative. Acceleration. T square's derivative will be 2t, so 2t I cap minus 4t's derivative will be 4, right? T raised to 1's derivative is it is 1, so it is just 4 j cap. Now once we get the acceleration, we can easily find the force. So now the force, which is m times of a, it will be mass, which is 2 kilos, multiplied by 2t I cap minus 4 j cap. So therefore, the force will be how much? 2 to the 4. So 4t I cap minus 4 into 2, which is 8. So 8 j cap. But let's substitute it at 3 seconds. So force at 3 seconds will be 4 multiplied by 3 I cap minus 8 j cap, which is going to make it 12 I cap minus 8 j cap Newton. Okay, so that much part I am done. Now the only part remaining is velocity. So how much is the velocity at 3 seconds? Velocity at 3 seconds, put 3 over there. So 3 square I cap minus 4 multiplied by 3 j cap. 3 square means 9. So 9 I cap minus 12 j cap. All right. So now it's a good time to figure out how much the power will be. So it will be the force multiplied by velocity at that moment. So the force is 12 I cap minus 8 j cap dot product with 9 I cap minus 12 j cap. Perfecto. Okay, so let's see how much does it come. For dot product, I with I, j with j. 12 into 9, that's going to be 108. And what is this? 12 into 8, which is going to be 96, but that is plus over here. Can you see that, guys? There is a minus here, there is a minus here, so it will become plus. So 8 into 12, that's going to be 96. Everyone with me? 156. No, bro, it is not going to be 156. Now you calculate and tell me how much is it going to be? Yeah. Welcome, Harsha. Yeah, what is the chapter next? Next is going to be center of mass, collisions, all of that. Okay, that's what we are going to go. Is that right? Yeah. And if you guys are not yet subscribed, please do that right away, right now. It's very important, or else you will start missing all our important classes. Okay. Yeah. Cool. Yeah. Then it is going to be 204. Very good. Hi, Kati. Yes. So this is going to be 204 watts. That is the answer. Perfect. Clear, everyone? How do we do it? Already did. Very good. Let's do another question coming up on your screen, and here it is. So what happens over here is that there is this mass which is dropped and it starts falling down, and once it reaches here, this is at some time instant t. There are two questions. Find number 1, power at time t by gravity at that instant, that is instantaneous power. Second, the average power, see how the instructions change, till, I'm using the word till the time t by gravity. Whenever the word comes like at or in this moment, then it is instantaneous derivatives. But when it comes like till this time or for this duration, then it is talking about average values. So you have to find both the power by gravity at that instant and till that instant. What is the average value? All right, so let's think. Gravity will act down, so mg will be down, because of which it will be accelerating like this. It would also have some velocity, I believe, at this moment. So that velocity, I will just put it as v. This is nothing but its acceleration. Okay. So if you want instantaneous value, what do we need to do? For instantaneous power, we need the gravitational force dot product it with the velocity at that moment. Gravitational force is simply mg. Velocity, well, we need to find it out, not that big a deal. We can find it out easily. V is u plus at. It was dropped, so initially 0, acceleration is g, time is t. So therefore, velocity is simply put g into t. So put it over here. Velocity is g into t. Dot product was there, but the force and velocity both are in the same direction. So obviously, cos of 0. Dot product is AB cos theta. A dot B is AB cos theta. So F dot V will be FV cos theta. Theta is 0 degree. So cos 0. Cos 0 anyways is 1. So this is just going to be M into G, which is G square into T. So that is the power at that moment. This is instantaneous value. Okay, this is instantaneous value. That's not all. We have to find average also. How do I find average? Let's think. For average power, we need the total work done by gravity upon the total time taken. How much time did it take? T, already known. What is the total work done by gravity? Well, work done by gravity, force is down, displacement is down. So if I assume this particular displacement to be h, so then it will be force, which is mg, into displacement, which is h, and angle is 0, so cos 0, upon basically time. But sir, you do not know h. What will you do now? Yeah, you are right, bro. I don't know h. We can find it out, not a big deal. How, sir? Again, use kinematic. S is ut plus half at square. The displacement itself is h. Initially, it was 0 speed. Half acceleration is g into t square. So h is gt square by 2. Substitute that over here. H is basically gt square by 2. Tt cancels, gg multiplies. So m g square t divided by 2. So that is average power. So such a cool problem which tells me how to calculate instantaneous, and this is telling me the average value of the power. The method is completely different. This is absolutely clear. Yeah, very good, Sandeep. It is half mgt square, exactly half of the instantaneous value. It's not like a rule that it should be half. It just came by coincidence. Okay, great. Let's do some more questions coming up on your screen, and here it is. All right. Sand is being dropped from a stationary dropper at some rate of 0.5 kgs per second on a conveyor belt, moving at some speed. The power needed to keep the belt moving with the same speed will be. Okay, let's see and understand what this question actually means. There is a belt, okay, and you are dropping some sand. Sand is being poured over here onto it. Every second, some amount of sand will get added and it has to acquire some speed. So how much power is needed? So in this problem, what is happening is, see, the speed is constant, but the mass is added, and because of that, what will happen? The kinetic energy will have to increase, and if kinetic energy has to increase, work has to be done. That is the reason why power has to be supplied. Power has to be supplied because some kinetic energy is increasing. So if I'm able to figure out how much is my kinetic energy increasing per second, I think my job is done. So the logic for this problem, I believe, will be the power will be the work done by the time. Work is the difference of the kinetic energy by the time. So kinetic energy, right? So whenever you are adding some mass, it was not moving initially. Suddenly it starts moving. Like these particles were not moving. They touch the belt, they start moving. So it is gaining some kinetic energy. So the kinetic energy gained will be half mv square starting from rest, whole thing by time. And now I can just do this m by t separately and v square over here. That's it. What is this m by t? How much mass is added per unit time? 0.5 kgs per second. Kgs on the top, seconds below. So how much mass is being added per unit time? That is 0.5, and speed is 5 square over here. So that's it. I mean, look at it. 5 square is 25. 25 5s are 125. 125 divided by 2 is 62.5. But because of the decimal, it will become 6.25 watts. That's it. So 6.25 watts, not 12.45. Okay. So that should be the answer. Is that right? Everybody with me? Yep. Perfecto. Perfecto. Amazing. Clear? Yeah. Just check this out. Just check this out. M into half gt square power is dm by dt 2.5. What is that 2.5? V into dm by dt. No. V into dm by dt. No. Half. This will be the average value of the power, my dear. Yeah. V into dm by dt is the force. Force into velocity, what will you take? No, no, no. Sandeep, that will not be the right way, because then what you are doing, I'll tell you why you're getting double and why the answer marked will be also different here. That will be the instantaneous value at the end of the acceleration. That grain will fall, it will start moving and acquire 5 meters per second. At the end, when it just reaches that final speed, that's when the instantaneous power might be 12.5 watts, but that is not the average power at which you are delivering the things. Okay, because then when you're choosing the velocity, yeah, when you're choosing the velocity, you are choosing the final velocity. Is that absolutely clear? Yeah, 5 square is 25. 25 5s are 125. 125 divided by 2. How much is it? Yeah. Yes. Yeah. It is variable mass system. But do you need the knowledge of variable mass? No, I don't think so. You don't even need the knowledge of variable mass. Directly, you can do it with a simple calculation. Is that clear? Yeah. So don't think that variable mass is deleted or anything. No, it's not like that. Variable mass can come in different ways. You don't need that rocket propulsion and all of it. That and all is not needed. Yeah. See, let me tell you one thing. Even though this 0.5 kgs per second is mentioned, a lot of students, very good, you asked it. Sir, should I not take the time interval as 1 second? Do you really think exactly in 1 second 0.5 kgs is dropped, or it's a rate which is given? It's a unit, right? So whenever this is mentioned, it's an instantaneous rate, 1.5 kgs per second. Maybe for 2 seconds, nothing will come. Maybe after 4 seconds, you are adding 2 kgs. Then again you are sitting silent. And then after 4 seconds, you are adding 2 kgs. Still the rate will be 0.5 kgs per second. So it's not that every 0.5, every second 0.5 kgs is coming. It just means that the rate at which it is coming, it's a unit. That's it. Okay. It's an average rate, you can say. Is that clear, Anonymous? Yes, Sandeep. वो average निकाला है, क्यों निकाला है? Why have we taken the average? Because the power needed to keep the belt moving. This power needed will now be average value. This power needed will be the average value. If you have to find instantaneous, then you need to tell me what is the velocity and what is the time instant when you want to find that instantaneous power. Here nothing is mentioned at what instant you want the instantaneous power. Because when you just drop that particle, the speed is 0, power is 0. Slowly it will accelerate. So every time the velocity will be different, power will be different. When it finally reaches the speed, then the power will be completely different. So that is the reason why we are calculating average value of the power. Okay, over here, this means the power needed, it is average value. Is this clear? Understood? Yes. No, it is not dm by dt which is given. Okay, it is dropped at a rate of 0.5 kgs per second does not really mean it is falling smoothly at 0.5 kgs per second. Like I said, it could be an abrupt thing. It is not necessarily that you can even take fraction of a second and you can see some proportionate mass falling. Like I gave the example, 0.5 kgs per second only means over here that either every second 0.5 kgs is falling, or every 2 seconds 1 kg is falling, or every 4 seconds 2 kgs is falling, or you can take even a bigger interval. It's just that the average rate is 0.5 kgs per second. Okay, is that clear, Dilip? Lot of people make some mistakes over here. I have seen that. It's a very common, such a simple question also. Many kids will make this mistake. They will do this by some what do you say, that I see if many people will do this. Okay, F is equal to uh, dp by dt, and then they will do this m into v, and mass is not constant, so v is outside, so v into dm by dt, and then they will do v. What is v? It is 5. And what is dm by dt? They will do this 0.5. So then this will be basically 2.5. This is the force. Now power is force into velocity. So force is 2.5. What is the velocity? 5. So how much will this come out to be? 12.5. Now, what is the problematic thing in this answer? This is not the right answer. Why? This is instantaneous value. This velocity is the final velocity. This force you are taken, okay, fine, it is constant. But this is the final velocity, so this is not average. This is instantaneous at the end of acceleration. And that mass falls and it accelerates towards the end, just before it has reached the final speed of 5 meters per second. That's what that power is. So this is not the right answer. Is that clear? This is the most common mistake. Many teachers also will do this, I'm telling you. All right. Moving on to the next question coming up on your screen. I'm so glad that these kind of questions come up, and best part is you guys are challenging the question, and you are asking those questions. Sir, I'm not convinced, and I'm very happy, and I exactly love this kind of things, because I love it when students make conceptual mistakes, and I love explaining, why that is wrong, why this is correct, because that is what the fun part is. Because unless you understand what that concept is, you will make those mistakes in the examination. Initial energy will be zero, no, anonymous. Initial energy will be zero. How do you know the initial energy? Because it was at rest, it will just fall. The ratio of the powers of two motors that are capable of raising 300 kg in 5 minutes and 50 kg in 2 minutes, respectively, from a well 100 meter is how much? Okay. So if I'm raising the water, I'm increasing the potential energy, I believe. So what have they asked? Power ratio. So power is work done by time. Here the work done is to remove the water from the well. So in increasing the potential energy, that means it will be mgh by time. Now they have asked the ratio of the powers, that means P1 by P2. So it will be M1 GH1 by T1, and here M2 GH2 and T2. But I'll tell you few things which are good, like G same, even the height is same. Yeah, H1 and H2, H1, H2 is 100 meters. So I'm just left out with P1 by P2 is M1 T2 by M2 T1. Interesting. So now it's easier for me to solve the question. So that ratio is 3 root x by root x plus 1. So I just have to solve this equation. What is mass 1? That is 300. What is time number 2? Time number 2 is 2 minutes. Okay, mass number 2, that is 50 kg. And time number 1 is 5 minutes. Sir, this is kg, this is minutes. Is it fine? Don't I have to convert minutes into seconds? Absolutely not, because on the top and at the bottom both are minutes, so the units will get cancelled. So don't waste your time over there. Anyways, let's solve this now. So what is this now? So see guys, this is 5 and this is 300, right? I'll do it for you. So this is just going to be 6 0. Okay, this 0 and this 0 will also cancel. So that's it. We have over here 6 2s are 12 divided by 5. Okay, perfect. Now let's move things around as per our convenience. So 5 into 3 is 15 root x is equal to 12 into root x plus 1, cross multiplying. Okay, so bring 12 root x over here, so it will become 3 root x is equal to 12. So root x is equal to 4. So x is equal to 4 square, which is 16. So 16 is the right answer, which is option number 4. Perfect. Okay, so this part looks scary initially, so something scary will be there, but actually when you looked at the question, it was nothing scary. It was so laddu question. Yeah, that is the answer. Perfect. Let's go to the next question coming up on your screen. The force is given by this, the power developed by the force at this particular time. Okay, I think we are now going to go to some integration questions or derivative questions. The mass is beginning to move under the force of 60 I cap plus 60 square j cap. The power developed by the force at an instant of time t is how much? Interesting. So, in one of the previous questions, velocity was given, we found out the force. But when force is given, to find the velocity, obviously you can't differentiate, you have to do antiderivative, which is integration. All right, so we have to find the velocity. That's the only option left with us. So let's do that. Now, to find velocity, we need acceleration. For acceleration, we have to just take the force and divide it by the mass. So when I divide this with this, so 6t I cap plus 6t square j cap, whole thing divided by the mass. Mass is how much? 2 kg. So that is going to give me 3t I cap plus 3t square j cap. That's acceleration. What is velocity? Velocity will be integration of acceleration with respect to time. And we are going to start with 0 to t, I believe. Mass begins to move. Okay. So from 0 to t. Okay. So let's do that. Integration 0 to time t. Acceleration is just over here. 3t I cap plus 3t square j cap dt. Okay, so this is going to be 3 is a constant, comes outside. T's integration will be t square by 2. This is I cap plus 3 is again outside. T square's integration is t cube by 3 and this is going to be j cap. 0 to t. So put t first and then put 0. This is what you are going to get. Absolutely. Okay, you don't have to break your head so much. This is the answer. But that is velocity. We have to find power. Power will be force dot product with velocity. So force is 6t I cap plus 6t square j cap, okay, dot producted with 3 by 2 t square I cap plus 3 cancels. So this will just become t cube j cap. Oh my god, crazy. This is purely mechanical. Chances of making silly mistakes are very, very high. That's all. Okay. Now 60 I cap and 3t square by 2 I cap multiply. So 60 multiplied by 3t square by 2 plus 6t square j cap and multiplied with j cap only. So that is t cube. So the power will be 6 by 2, 3. 3 3 is a 9. So 9t cube plus this will become 6t raised to 5. So 9t cube and 6t raised to 5. That is the answer. 9t cube, 6t raised to 5 watts. Perfect. We got it. Okay. So this was a question where integration was involved instead of derivatives. Option D. Perfect. Amazing. Amazing. Yeah. Let's go. Let's go to the next question coming up on your screen. Here it is. This one. So the body is moving in a direction with a force of constant power. The displacement is proportional to. This was a very famous question. This has been asked multiple number of times. Power is constant. How will displacement change with time? So now start with the basics. Power is force dot velocity or force into velocity. Same direction, so the dot product will not even change. So no need to put that dot. I'll just put FV. Power is constant. Keep that in mind. What I'll do, force I'll write it as m into a into v, and acceleration I will write it as dv by dt. Now once I wrote this, I will take dt on this side and mass on this side and see what will happen. So it will look something like this. V dv will be power by mass into dt. dt have taken here, v dv have kept here. Reason is power and mass are constant. Time is a separate variable. Velocity is a separate variable. I have separated the variables so that I can solve them. And the obvious thing to do right now is to integrate both the sides, yeah, from 0 to v and 0 to t, and see what do you exactly get over here. V's integration is v square by 2. Putting 0, you'll just get 0 square by 2. P by m is same. And here dt's integration is t. Putting the limits, you'll get t minus 0. So basically, you are getting v square by 2 is pt by m, but I'm not satisfied yet. I have to go to displacement. So move things around. So let's see what can we do. V square will be p, or rather 2p divided by m into t. Therefore, v will be equal to root of 2p by m into t raised to half. Perfect. And now I have the option to write velocity as dx by dt. Velocity as dx by dt. Perfect. So once I get this, I'll write dx is equal to, this is some constant, doesn't matter, 2p by m, t raised to half, and I'll shift dt over here. Again, variables being separated, obvious thing to do is integration, 0 to t and 0 to x. That's it. So dx's integration is x only. So x minus 0 rather, after the limits. Root t, 2p by m is a constant, so forget it outside the integration. T raised to half's integration is t raised to 3 by 2 by 3 by 2, and then put 0 raised to 3 by 2 by 3 by 2 and all of that after limits. So x will be that 2 goes on the top, 3 comes below, root of 2p by m will come, and this will become t raised to 3 by 2. This clearly suggests x is proportional to t raised to power 3 by 2. So times power is 3 by 2, which is third option. Perfect. That is how you can solve this question as well. I doubt you can change it, but it should not be much of a problem. Just register with 2 numbers, maybe that will be better. Yeah, register with 2 numbers. Yeah, for MVSAT. Right. So that was the question, guys. A very similar question I have for you. And oh my god, the answer is marked already here. What can I do? 1 second. Yeah. So take this question as homework, because again, it's a very similar question. I'm pretty sure you will be able to solve it. Okay. So here again, some dm by dt belt type of question is there. So think carefully how you are going to solve. I've showed you both the methods, the correct and the incorrect methods, in one of the previous problems. If P is the power delivered to run the belt at a constant speed, at which of the following relationship is true? Okay. So try to solve this particular question and make sure you put the correct answer in the comment section after the session is over. Is that right? Okay. So that was the final question as homework. We have solved all the questions on power, mechanical energy conservation, and even problems where mechanical energy is not conserved. So this completes the chapter. We have also done potential energy graphs, finding maxima, minima, stable, unstable, equilibrium, right? We have done conservative, non-conservative forces, literally all kinds of concepts we have covered in this chapter. It's a big chapter, but it's a easygoing chapter, and it's a, I would say, base chapter for all the other chapters, be it for 12th or even for 11th. Okay, so do it properly. Next we'll do a center of mass. We also have to do circular motion. We'll continue with that, right? Take care. Bye bye. Captain Shreyas signing off.